Okay. Thanks for joining. Let's get started. I'm very well aware that I'm standing in between the conference program and your beer. So let's try to finish in time. My name is Simon Kaufmann, or Simon Kaufmann. I work for the Deutsche Telekom in the KiwiCon project, which is a smart home project where we are developing a smart home solution. I'm working there as a developer evangelist, mainly as a committer of the Eclipse Smart Home project. And while doing so, we happened to experience some really nasty bug, which I thought would be a good storyline that we can use to have a quick look into several different methods and ways how to analyze memory, especially as this was needed on such a constrained gateway. So first of all, what is the edge? In smart home solutions or generally in edge computing, what we're doing there basically is moving cloud computing back onto customers' premises, like back into the homes. So there's some smart devices running, spread everywhere at home, like smart bulbs, vacuum, robots, lawnmowers, something like that. They all speak different protocols, and there's a small box, like a gate, we call it gateway, which is placed inside the home, which can speak all these protocols, has some radio chips integrated, runs some decent logic there, so it's more than just simply like a protocol translator or anything. So there's really some Java code running there. On the other hand, there are some user interfaces, mobile devices, whatever, which are connected to some cloud services, which then get back onto the gateways. So in our case, these gateways look like these here. We have several different kinds. What they all have in common is that they are capable of running some decent Java stuff there, but it's not much that we get there. It's not like programming on the server side where you just simply buy bigger boxes, put more RAM in there. We have to live with these constraints. Like we're getting only a little bit of flash memory when running on a router. We're getting just a little bit of RAM, and we have to squeeze everything in there. Our operating system, the Java runtime, and of course our code as well. What makes it especially hard when you have a problem on such a gateway is that it's not running in a data center. So you can't get there, you cannot just plug in your cable next to it in the same switch. You would need to go to some customer's home, ring the bell saying, "Hi, sorry, Deutsche Telekom, we would like to analyze a problem." So that's definitely not an option. But we are running code there. We are running Java code there. So we actually experience the same bugs, the same situations that you could run onto like on server if you're running on servers. And there is some personal data involved. So the data privacy laws, they also put some restrictions on what we are allowed to do. I mean, we can't simply push all the log files and everything onto our servers, because that, would make everybody, including us, pretty unhappy. A quick, very brief view on what's running there. We have a Linux stack there. In this case here, what I would like to talk about today is this. There's an Alpine Linux in a customized way, not really like out of the box. They put some glibc there. That's something we buy from the hardware manufacturers. In addition, we were running Java 7, and while we're talking a lot about Java 9 today, we were really happy that last year we could finally manage the upgrade to Java 8 Compact Profile 2. So it's not even a full JRE that we can run on these devices. On top of that, there's an OSGi runtime running, in our case a commercial one, and on top we put some Eclipse Smart Home and some proprietary stuff that we built in order to make it more usable, more user-friendly than what is there in the open source space. So when we're talking about bugs, we need to be aware of bugs, or we need to get made aware of bugs. Of course, we have several unit tests, we have lots of integration tests, we have a quality assurance department which they test manually, or they're working on automating most of the stuff. Like they behave as real users. They do all that, they report bugs if they find any. Everything is good. We have beta users who are really friendly, they report everything that doesn't work well, which might have slipped through the quality assurance, but these guys are really great together with the unit tests. We're mostly fine. Anyway, we're all developers. We know sometimes there are even bugs in production that made their way through all these 4 steps before. They get reported. Somebody calls the hotline, says, well, I have a problem. There's primary support that they help them, and finally they file a bug. And in addition, there might be just coincidence. Something you just see. And we're trying to make this coincidence a little bit more structured. We have log files, which we can at least use in the first stages like development, quality assurance. There we have full access to the log files, we can use them, we can analyze them. We have some automated failure reporting, so whenever errors occur, it gets reported to a central system. We'll look into that in a minute. And we can also do some metrics monitoring, where we see if the whole crowd of gateways is happy or not. The problem with the log file is that it requires active analysis. So you need to be aware of a certain problem, then you can look into it. You have the data privacy issue, means you cannot look in production in just some random log files, but you need to be made aware of a certain problem, and then you can do it for the analysis. It's excellent to have, but not sufficient in every case. That's why we set up the so-called ELK stack, like Elasticsearch, Logstash, and Kibana, which is basically integrated into the OSGi runtime. It takes every error, every exception that occurs, sends it to the Logstash that does some crunching on it, puts it into an Elasticsearch database, and then again there's this nice UI, Kibana it's called, where you can filter for it, search for it, have an analysis over several log files or error reports. Which is really great, but we still have the data privacy issue. So if whenever you go to the toilet and switch on the light, and that would cause an error, we would see when you go to the toilet. So that's not an option in production. That's why we don't do it there. But nevertheless, for all the development environments and quality assurance environments, we have that, and that has been of really huge value. Another thing that we are using is Sentry. I don't know if you heard about it. That's really good to manage crash reports, or to do some aggregation on crash reports. It's mainly used in the UI realm. They attach lots of context information there. So you have everything that you need in order to fix a bug. And their claim is that they fix errors even before the quality assurance guys manage to write a bug report. So it actually worked a couple of times that they were even faster, but nevertheless, it's always easy then to spot the root causes and have everything like the context, the data that is required. But that, of course, requires that when writing your application, you attach this context so that you anticipated that an error might occur in that situation, which is sometimes good if you're talking to some smart devices and you know this communication might fail, and you expect that you need some more data in order to analyze why that is. So we can use it in Java too. It's good. Nevertheless, it's definitely a problem with the data privacy, so we cannot use it in production because of this whole context that we attach. We know the state of the whole house, basically, in order to analyze the bugs. What we are using in production pretty successfully is Prometheus together with Grafana. Prometheus is a matrix collection server Don't know if you heard about that one. There are other products as well. Prometheus is open source. And that makes anomalies easily visible. So you see over the last hours, like how many HTTP requests you got in the backends, how many of these gateways actually are connected to the backend. For example, here you see a little dent in there. There must have happened something. In that case, it was an update, so it was all fine. But you immediately spot anomalies, which is really great. And in that case, as you just have a look at, or as you're just monitoring the whole, the system as a whole, there's also data privacy, or it's not such of an issue with data privacy. So that's really great. It's very well known in the server world, but it can be used on embedded devices as well, just to push metrics up to a central Prometheus server. So now, one day it happened that in our Kibana instance, we saw this. We saw out-of-memory errors in different locations or on different occasions. The only common pattern that we found is that they somehow interacted with the operating system, so they do some native calls. But it's completely unclear, or in the beginning it was completely unclear to us, whether all these things here actually are only victims, like there is no memory anymore, that's why they cannot work, or if they actually have a memory leak and that's why they might be the culprit. So everybody here is a suspect, but we simply don't know what made that happen. Our first approach to that was, well, let's first gather all the observations. That's why we have this nice Kibana instance, and see where it happened and how often it happened, if it depends on a certain gateway type, if it depends on a certain whatever, a certain environment, on a certain version that is deployed onto it. So we had all this information. We saw that in development stages, we saw almost 10 devices which had this one of these out-of-memory errors in the last 2 weeks, I think. But we have seen none in production, which is not that much of a surprise because we are not monitoring production that closely. But, of course, we have some samples running on production where we put this monitoring into, because they're sitting in our offices. There we don't have the privacy issue, and also the QA is doing that. So there would have been a chance to see it in production as well. Nevertheless, we haven't seen it. So our first attempt was that we think about what are these differences, like to find a common pattern, what could be the root cause? Maybe that narrows down one of these places. So we thought about different firmware versions, different security measures, because on production firmware you can't get into there. On development firmware everything is open, it's easier for us, otherwise we cannot develop. And so on. So a few additional bundles or newer bundle version were deployed in development stages. And of course, while developing, you all the time do frequent updates. And that was a promising suspect. So we looked into the update cycle, and what could have been better than tracking what during an update cycle the JVM does. There's a really, really useful tool now integrated in Java 8. Who has heard of the Java Mission Control? Perfect, so we don't need to go into too many details. It basically gives you a pretty good profiler, a pretty good memory tracker for free. It's just there. The only problem is it's not available on Java compact profiles. So while it would have been easy to use it on a Mac, it was completely useless at first on the gateways. So what we then tried is to prepare as much gateways as we could get our hands on with a full JRE. We had a full JRE, we downloaded we built it for the ARM, and managed to put it on, at least for the development firmwares, and we have seen that with development firmware, so that was good. We just put it there and kept them running in the hope to see this error again. But of course, all the time we were not sure if that spoils the party, if that bug really still occurs with this full JRE. Maybe it was a bug in the compact profile distribution, or whoever compiled it, and could have been something wrong. But so there's always a risk if you tamper with the environment that the bug suddenly disappears, especially if it's a bug that you cannot yet reproduce. While we were doing that, and while we kept some running, we did a lot of update cycles just in the hope to cause the same bug or to cause this error. So we did over 24 hours, we did as many update cycles as we could, and I just tracked here one, and the Java flight control, the mission control has one feature to track the class loaders. So we see how many classes were loaded, and here you see one of these update cycles, and here you see how many of these classes have been freed again afterwards. And obviously there's a difference. There's about 2,000, here about 1,000. So there's something leaking, definitely. We fixed that, or we found the place in the logging where one of the SLF4J classes have been kept in a static variable. We fixed that. Afterwards, the update process looks fine. So 2,000 plus, 2,000 minus, all good. I reported back to management, hey, we fixed it, you can go on with the rollout of the new firmware, all is good. This is another useful thing of the management console. So you see here also, it does some profiling, or it does some measurements, parts of the profiling for which thread has been was stuck. So we saw here that we spent lots of time in our own OSGi to SLF4J bridge implementation. We found some synchronization which was actually not needed. So it was simply there because somebody was too cautious. We removed that, and that was one of the benefits that we actually took the time to look closer at it. So that's a really, really valuable tool, especially as it comes for free. There might be better profilers out there which help you more to find the root causes, but this here is excellent to see where you spend most of the time. So remember, we did the update of Java 7 to Java 8. We learned that in Java 7 there was a permgen space. In Java 8 it's not there anymore, so the meta space where the classes are loaded into is basically shared with the native memory that the JVM can use. We thought, well, we fixed this class loader issue, so the classes don't fill up this meta space anymore. It makes perfect sense that we now don't run out of this native memory anymore. All good. We were happy. On the other hand, sometimes you just got to be lucky, because shortly afterwards we reported everything is green. We rolled out this new firmware, so now it was live in production. Shortly afterwards, our Kibana instance was moved. We had a nice little domain name, whatever that in reality was, something like that, and it was moved to another cloud instance where we didn't have a domain pointing into there for whatever organizational reasons. We just said, well, it's okay, we have a static IP, let's use this static IP. So on some home bases, or some of these gateways which were connected to production, we saw an unknown host exception there, which only works if you don't use DNS resolution to report to your Kibana. So we were really lucky to see that, otherwise that would have never ever shown up in any of our reporting or monitoring systems. So it's services.kiwicon.com is our domain. We were pretty sure that our domain servers were not down, so that doesn't make sense that this domain is unknown. We looked closer, scanned our Kibana, and even with this new firmware, with this fixed class loader issue, we also saw occasionally a good old friend, meaning we saw out-of-memory errors again. Most of the time connected with a deflator, but it doesn't have to be. It was everywhere again. It was a real problem because now we knew it's live, it's in production, but so far we hadn't have any customer complaints. Nobody called the hotline. All looked good. That's why we did went further, did some statistics. We're looking at how many gateways were affected in the last 2 weeks with out-of-memory error, how many with the unknown host exception, and correlated these and found out gateways which had this out-of-memory, all of them also had this unknown host exception, which to me sounds like a pretty good correlation. The other way around, it didn't work that well. So if you had this unknown host exception, it doesn't necessarily mean that you also had an out-of-memory error. But that was something to have a closer look at. Now, as I mentioned, we only saw that in our development stages. So we have development firmwares here, we have production firmwares here. Some of them are connected to our development backend, some of them are connected to our production backend. As I just said, we also saw it on production firmware, but they were all connected to our development backend. We were in a stage where they wanted to roll out or start some marketing campaigns, and our managers were a little bit nervous, and we said, well, we might have a problem in there. So how many customers are affected? And we had to say none, because nobody reported any problems. We were simply not aware of anything, which happens if you respect data privacy. Luckily, we have been rolling out that monitoring to our beta customers as well. And finally, we saw somebody who had the same connected to the production backend. So the larger your net is, the more fish you catch. We caught one. Who knows the memory analyzer? Perfect, then I will skip quickly over it. The memory analyzer is an Eclipse project, which is a really great tool for looking into the heap. So you can do heap dumps from a running system. There's a command line tool. Unfortunately, it's not available on Compact Profile 2. So again, we were somehow stuck with either using the full JRE, or what we then did is we simply developed a bundle which then triggers the heap dump from inside, and also added a backdoor to our development system so we can simply upload it even if it's a production firmware. This is typically good to discover places where you are wasting memory by allocating objects and keeping references to these objects so that the garbage collector cannot do its job. Here I put simply the command line tools, how that works, but there are basically 2 or 3 terms you need to remember, or you need to know when working with this memory analyzer, because it's pretty much straightforward. You simply open such a heap dump with it. You see for each object that you find in there, you see the shallow size, which is the size that an object takes by its primitives plus the pointers to other objects. So it's just the size this object occupies itself, but not the size it has in total with all its reference children. That would be the retained heap. So that's the one we need to look at, because that aggregates the size of the object itself plus the size of all other objects transitively, which it's referring to. And the other way around would be incoming references. So if you want to know why an object is still kept alive, who has references to it, so the garbage collector does not get rid of it, these are the incoming references. Can have a quick look at how it looks like. I've prepared here, I hope you can see it. It's a little small, I will try to zoom in. So you see here a histogram where you see all object types that are in the heap, and you see how many of them are there. And that was just a very simple Hello World example where I just stuffed 1 million strings into an array list. And there you can then see, figure out for such an object, list objects with incoming references. As I said, if we want to figure out why an object is still kept alive, we only have to look at the incoming references. And you can see here individual instances and dig in there and find out who is having references to them. So here's this array list where the string is stuck into. And this array list apparently is a field or a variable called call collection in the class collection leak MAT. So this here is a very, very simple example of how to spot such a reference to a leaked class. I can assure you, if you do it on a real heap, there will be many, many more objects. So the forest around one tree is a little bit bigger, but in such a case, in out-of-memory errors, you're looking for outliers or anything, so you will easily spot if something like that went wrong. However, in our case, that didn't help us at all, because our heap was perfectly fine. So there's plenty of heap space available, and still we saw this out-of-memory error. We did some research, and there are a couple of examples in Java where you actually can really, with a Java class, waste native memory. The deflator is one of these examples, but because the deflator does some native calls to some shared object library on the operating system, because the operating system actually does the real compression and decompression. It's not implemented in Java. So whenever you create such a deflator instance, there is some native memory reserved. Well, we were looking for an instance of that. It's used in the compressed HTTP client, of course, and we're trying hard, firing thousands, millions of requests to such a poor gateway in order to somehow reproduce the same error. Of course, it didn't work. So we looked further. What can we do in order to figure out who loses all this native memory? In the Java 8 JVM, there's this thing called native memory tracking, which you can enable. It has pretty much zero overhead. And you can, with that, you can trigger, or you can set a baseline like that. So this is how you enabled it. With that, you can set the baseline, and then after doing something, after some time, like after doing an update or after waiting for 24 hours, you just do a detailed diff in order to figure out what it did. You get such a nice report. There is no use in doing that live now. Let's quickly zoom in. Yeah, sorry. So it even does some native memory tracking. It tells you how much, compared to the baseline, how much additional memory the JVM allocated. It looked perfectly fine as well, because this is the native memory that the JVM reserves itself, like for his own things. If it calls another shared object library, it doesn't track what this shared object library does. It's simply not possible. So it's useful if you want to analyze if the JVM does something wrong, or if the garbage compiler reserves too much memory or whatever. So you see all the details here, but apparently in our case it was not a deliberate misbehavior of the JVM. Anyhow, if you're suspecting something, it's worth looking into it. Well, then we thought maybe another approach would help. We tried to look at the memory itself. Recent Linux kernels have some countermeasures against doing that, because that's of course a security leak. So you cannot simply, or you cannot directly dump the memory of a process anymore. It was possible in older versions. But we found another trick. If you simply put something into the RAM that forces the operating system to swap,
Then you can easily get access to the memory because you can read the swap just with dd. We used the strings command to figure out what strings are in there. We sorted them. We tried to find the unique counts of every string. We found a couple that looked interesting, like KiwiCon was in there a couple of times, but nothing that led us to anything helpful. Enter jemalloc. jemalloc is a pretty cool thing because it's a shared object library that implements memory allocation. Normally you would use the glibc in our case, but with a simple configuration, like setting these environment variables, you can make it, you can first make use of this library to allocate memory, and second, it has a really great feature for tracking or for printing out what blocks of memory are allocated. So some native programs like Firefox, for example, they use it for memory allocation, but we try to use it just for figuring out who allocates memory. So we're mainly interested in this tracking. It prints out something like puts something into a file. There's a jeprof tool which you can run and get some detailed analysis. I used here a Hello World example again. So you see here that somehow, I mean, you don't see really the Java classes, but still it's amazing. It's close to something that we recognize. So you still see here that's the deflator in it that allocates memory. You see here how much memory it directly reserves and what's the retained memory, because this zip deflator again at the end calls the deflate init too, and that's actually what allocates all the memory. So in this case here, I did this hello world in order to produce a memory leak with that. Still, unfortunately, that was not the case here. The real solution actually for this presentation is not that interesting. The interesting part was the journey. So what in the end we saw, or we noticed while doing all this memory dumping, swapping, everything, we saw, I'll make it a little bigger here. We saw these two numbers which were interesting, the resident set size and the virtual memory size. The resident set size is the memory that a process really occupies in the RAM. Like that is something that is used, that is allocated, that is used, where there is something valuable in it that the operating system cannot compress or just ignore because it was allocated and never used. If you just allocate something and never use it, so the glibc or jemalloc, whoever, they go to the operating system and they reserve blocks for themselves. And then they allocate for certain variables or whatever, whenever they want to put something in, they then really allocate a certain amount of this huge block. So you can keep allocating, not using. And you might remember from the good old 32-bit operating systems that this is a very interesting number because you simply run out of addresses. It's not, this number doesn't mean anything. You can increase it as much as you like until the 30-bit integer variable is at its end. So the operating system has no memory to allocate anymore. It turned out that's what happened. There was a bug in the glibc that they put into our firmware update that we were not aware of this update because we were so much focused on the Java 8 update that we simply forgot to check the other updates or other changes in the firmware. And unfortunately, this version slipped into, nobody was at that point aware that that was so buggy. By the way, this hit us especially hard because did you know that there's a DNS cache in Java which you can disable? And of course we did that because we had some on the operating system level, so we thought it's not useful to have a second cache in Java, so we disabled it. So for each and every HTTP call, we did a DNS resolution, which was a call to native library to the operating system. That's why it hit us so hard. So, as a summary, the important thing is,
as we cannot have a direct access and we cannot look into such a gateway, we need to be aware of what's going on there. With different privacy levels, different security levels, we need to get as much information out of them using Kibana, Sentry, Prometheus. Another thing is, for analyzing it, we use memory analyzer for looking to a heap. We can use native memory tracking to figure out if the JVM behaves well. You can use JEmalloc to check if there's memory allocation going wrong. Unfortunately, in our case, if the memory allocation library itself has a bug, it doesn't help replacing it with JEmalloc because there it works nicely. In any case, this blind spot that we have now that we, with the edge computing, that we moved the cloud or distributed the cloud into very remote places, remote from the sense, in the sense of us developers, we really need to fight this blind spot. That's the most important part in tracking down such weird errors which just occur randomly and cannot reproduce in unit tests or anything. Thanks a lot. If you have any questions, I will be here. We can have a more detailed discussion over a beer as well. Thanks a lot.